Here are number 24 and 26 from section 4.1. In this set of exercises, we're to find the extreme values of the function and where they occur. But notice that the problems themselves seem to have a little bit of less information than the problems prior to this set. Notice there is no domain. So I think initially we're going to hang on to the graph of this one or lean on the graph of these functions quite a bit until we get to the point where we can do some calculus. So for number 24, y equals 1 over x squared minus 1, I've got it queued up in Desmos. And notice that this function seems to be defined everywhere except two places where it has a vertical asymptote. That looks to be at about -1 and +1. And if you notice the function itself, that makes a lot of sense. -1 and +1 would both make the function's value undefined. So I don't believe this function has an absolute maximum over its entire domain. Notice the function just grows without bound as it approaches its vertical asymptotes. And the same with an absolute minimum. There's no absolute minimum because this function decreases without bound as it gets closer to both -1 and 1. But I do believe there is a local maximum at x equals 0, and it appears to be right around -1. And we know that local maximums and minimums can only occur at critical numbers. So let's make a point of finding the critical numbers of this function and then proving for sure that we do have a local maximum value there. So let's take a look. Number 24. I'm going to rewrite the function to begin with not as 1 over x squared minus 1, but as the quantity x squared minus 1 to the power of -1. Rewriting it this way allows me to use the chain rule to find the derivative rather than the quotient rule with a chain rule inside. Usually that makes work a little bit neater. So the derivative of this function y prime is going to be -1 times the quantity x squared minus 1 to the power of -2. And then we're going to multiply by the derivative of the inside, which is 2x. Finally, we're going to simplify this. A negative and a 2x stays in the numerator, -2x, and then in the denominator goes the x squared minus 1 quantity squared. So critical numbers out of this derivative. Is the numerator ever 0? Yes, it is when x is 0. Is the denominator ever 0? Yes, it is when x is plus or minus 1. But remember, we've already discussed the x values of 1 and -1. Those are vertical asymptote locations because the function's value is undefined there. And we saw it in the graph as well. So really, x equals 0 is where we found the critical number to be. So what is that maximum value that we looked at on the graph? Well, let's just try plugging 0 into the function, getting the y value. So y of 0 is 1 over a 0 squared minus 1. So that's 1 over -1, and that's -1. So on number 24, we can say that this function, well, I was about to write absolute, but that's not right. We don't have any absolute extrema, but we do have a local maximum value of -1 at x equals 0. And let's look at that graph one more time and confirm 0, 1, and Desmos will tell us that, yep, that's a local maximum at x equals 0 of -1. Let's do the same thing for number 26, 1 over the cube root of 1 minus x squared. And I have that one queued up as well. Let's hide the first graph, view the second. So it looks very similar to the previous graph, but almost inverted. We have vertical asymptotes at 1 and -1 again. That makes sense because 1 and -1 would make the denominator of this function 0. We also seem to have a local extrema where x is 0. Now this time it looks like a local minimum because that's at the bottom of a valley almost on this top branch of this function. I don't believe we have an absolute maximum because this function grows without bound. No absolute minimum because it decreases without bound. Does both of those things around the vertical asymptote. So since local extrema only occur at critical points, let's find the critical point of this function and make sure we do have that local minimum value. So for number 26, let's rewrite the function first. Now, keep in mind that a cube root is the same as saying to the power of 1/3. So I'm going to rewrite it as 1 minus x squared to the power of negative 1/3 by bumping that entire base up to the numerator again. And that's just like number 24, going to make the derivative easier to find. This is y prime now is negative 1/3 times a 1 minus x squared. We're going to take that negative 1/3 and reduce it by 1. So now that's negative 4/3. And then by the chain rule times a negative 2x. So simplifying this, I see negative 1 times negative 2x. So that's positive 2x in the numerator. In the denominator goes the 3 from the 1/3. And then that base 1 minus x squared. Now that's to the positive 4/3 value. Do we have critical numbers? Yes, we do. We've got x equals 0 from the numerator. And where is that derivative undefined? That's at x equals plus or minus 1. But just like number 24, plus or minus 1, not in the domain of the function because those are vertical asymptotes. So x equals 0 seems to be the only critical number. What's the value of the function there? Well, y of 0 will look like this. 1 over the cube root of 1 minus 0 squared. So that's 1 over the cube root of 1, which is 1. So we can say here we have a local minimum value of 1 at x equals 0. And one more time to the graph to confirm, Desmos should tell us, yep, that's the 0.01. So the value of the function is 1. It's at x equals 0. And that's a local minimum value. And that's everything there.